Welcome, Hornets. Today we're going to be taking a look at area under a curve and see how that works. So basically, I'm going to take just any curve, and you'll notice it's nothing spectacular. I'm going from A to B. Now, the basic idea behind this is if I'm trying to find the area under that curve, then I've got a few options. If I divide the curve up into just one rectangle and I go straight across, I might not get a very good estimation. But if I break this up into smaller pieces and I use those as rectangles, now the more rectangles that I make, the better my approximation. Now I'm not doing too many, I'm only doing 8 here. Keep in mind that ultimately we want to go to an infinite. But what I'd like to show you with this is how we can use rectangles in order to get a close approximation to an area under a curve. And I'd like to show you the relationships behind those methods. So let's go ahead and start off by thinking about this as getting less than. Less than is going to be best made by inscribed rectangles. Now, inscribed rectangles means that I'm always going from a low point over to a vertical that has a higher point. Notice that all of my rectangles are below. We're talking about an inscribed rectangle, and I'm going from each value on my interval from A to B and going up, so each of these are values plugged in, and this small little gap here, that small gap is called delta x. And delta x is made up of the number values, the endpoints, b minus a, divided by how many intervals? And I have 8 intervals here. So I've got 1, 2, 3, 4, 5, 6, 7, 8. So 8 is my denominator. And this is give me the size. Now, each of these points that goes across is made up from the very first value plus delta x added over and over and over again, where I is going to be an element from either 1 to let's start with 1 to 8. Okay? We'll just leave it like that. It's not the best notation, but it'll do for now. Let's make it at least interval notation. And so it's on the closed interval 1 to 8. And now I feel better. Okay. Now you'll notice we're starting to get a pattern here. And it's all about pattern. Now I'm going to call this value that is somewhere here some x, and this x is going to be called c sub I. Okay? And c sub I is defined as our initial value plus a certain number of delta x's. Now, if I want to do the same thing, but I want to get an over approximation, I'm going to go ahead and circumscribe the rectangles. It means I'm going from a high point and I'm making sure that my box, whatever box I'm using, is above, so that horizontal in the top of the box is above the curve. Notice that we now have that inscribed and circumscribed. So if I have a curve, let's just make it a simple curve where I have two different heights. The inscribed is below, the circumscribed is above. And because we're talking about it changing from increasing to decreasing, it's entirely possible that we have two below that use different values and that one height never used. Okay, so just be aware, always below, always above, inscribed, circumscribed. Making an upper sum, a sum that's actually greater than the actual integration, and a lower sum that's less. So we're now looking at a group of rectangles that are an upper and a lower sum that are less than, I suppose they could be, or equal to the actual amount from a to b of whatever function we're using dx, which is less than our upper sum. Now, one of the things that we're going to start talking about is how we write this sum as something useful. And we're going to take a look at that in terms of summations in our next video. But for now, just be aware that the integration of a function from a to b is the area under a curve, and that area is going to be found by finding rectangles either above or below, inscribed or circumscribed, and that will produce a sum that is either greater or a sum that is less than the actual amount under. Thank you very much. I hope this helps, and in the next video we'll take a look at summations. Please be well and take care. Bye-bye.